Hello everyone, welcome back. Today what we will do is continue our discussion on PCA, and last time we said that we will look at one example for PCA, a real-time application, real-world application, and we'll also look at some issues with PCA, and that will lead us to something more interesting, which not only fixes the issue but also gives us a general idea which can be used for many supervised learning algorithms that we will see later on. But before going there, let's start with a very interesting real-world application of PCA, which is called as the Eigenfaces application. So, what is this application? So, to look at this application, let's look at this example. So, this is a real-world example, which is called as the YALE phase dataset, the extended YALE phase dataset, and the reference to this dataset is right here in the Washington University's website. So, it's just a bunch of images of faces which are of the same size, right? So, all facing the camera images, all grayscale images, and around 20,000 of them. So, that's what this dataset contains. Now, how do you convert an image into features? Well, the way that this is done for the YALE dataset is a very simple idea. You treat the image itself as a bunch of pixels. So, basically, each image consists of some m cross n. You can think of it as an m cross n matrix of pixels, and each pixel value is a grayscale value, which is some number between 0 and 255, and now you can vectorize this whole matrix, m cross n matrix, into a vector of size m into n cross 1, right? So, so when you do that, so there are around 32,000 pixels. I'm not putting the exact number here, it is around 32,000, maybe slightly more. That doesn't really matter for our discussion here, but there are around 32,000 pixels in each image. So, each image becomes a point in a 32-dimensional space. Now, the question is, well, if you want to get a compressed representation of this data set, right? So, can we use PCA to do this? Basically, you treat this as a data set containing 20,000 points, 20,000 faces, and each point is a vector in 32,000 dimensional space. Now, what you could do is just run your standard PCA, whatever we have seen so far, that is, compute the covariance matrix, look at its eigendirections, and each eigendirection is now going to be in the feature dimension, right? So, the covariance is a D cross D matrix, so which means it will be a 32,000 cross 32,000 matrix. If you look at the eigenvectors for it, so that they will also be in 32,000 dimensional space. So, the best line that fits will be a line represented by a vector in 32,000 dimension. Now, what you could do is the following. You can now again convert this 32,000 dimensional vector back into an image and see how that looks like, right? So, the way we went from images to 32,000 dimensional points was map this m cross n to an mn cross 1 dimensional vector. Now, you can do the same thing in the reverse as well, right? So, because there is a specific ordering for these coordinates, where you converted your m cross n to mn dimensional vector, you can go back as well. And if we did that, we can ask, how do these principal components look like if I visualize them as images? And when you do that for this data set, you see the principal components look like these, right? So, basically, the first principal component looks like this image right here. The second principal component looks like the PC2 second image, and so on. Now, let's pause for a second and see what do these principal components intuitively mean, right? So, why are they looking like the way they are looking, right? So, basically, PC1 kind of captures the direction which has the most variance in the data set. That's what we saw PCA does earlier. Now, if you convert this into an image, so it is as if this is like the best prototype image that captures most of the variance in your data set. Because this is a data set full of human faces, so now this image captures the faceness of this data set the best possible way, you could say that. Now, as you look at furthermore principal components, what you observe is that you get more and more details that get added to these directions, right? So, So for example, PCK, which is some kth principal component, now has a much more, in some sense, a nuanced representation. It captures much more details, right? So there is, the nose is more clearer, the mouth is more clearer, and so on, right? So so now why does this happen? Because what is common for most of these data points is this template. This is the most common template. In some sense, this is where most of the variance is. But then as you look at other directions, they are trying to find out other characteristics of these data set, which are also important, which is where more and more details get added as you increase more and more principal components. Now the question is, what do we do with this data set, right? One question is, right, so let's say if you want to build like a face recognition system for the employees in a company or something like that, where you have 1,000 employees, right? So, or in this case, 20,000 employees. Now, do you really want to store 32,000 numbers per employee to capture that person's photograph, right? So 32,000 pixel details. Do you really need that, or is there a lower dimensional representation that perhaps represents what we want really well, right? So now PCA would tell us if that is the case, right? So now what we will try to do now is we will increase the number of principal components that we will retain, or in other words, the number of rounds we will run the algorithm for, or in other words, the number of eigen directions that we are going to retain. All of these are exactly the same things in our context. And now we will try to reconstruct the image, the proxy for these images, using only these retained principal component. In other words, what does this mean? This means that if I just retain one principal component, then for each of these images, I am going to take that image, dot product with the first principal component, that will give me a number. And now to reconstruct the proxy, I will multiply this image with just that number, right? So all the images will be some scaling of this number. Now if I am reconstructing with two images, it means that I'll take the dot product with the top two eigen directions, principal components, and then I'll linearly combine these dot products using with these images to get a new image, right? So now the question is, as I increase the number of eigen directions, how do these images start looking like? And that the YALE folks did that as well, and what you see is something like this, right? So for example, let's focus on the left hand side image first. Now here is a test image, right? So let's say this is an image that is not in your data set. Maybe again in a face recognition context, this could be some person who walks into your company, and then your inbuilt CCTV camera or something like that clicks a picture of this person, and then you get an image of this sort, right? So now what you're trying to do is you are trying to reconstruct this image using only the top few principal components. This is the image reconstructed using just 25 principal components, the next one using 50, 100 and so on. Now focus on the original image and the reconstruction using 1600 principal components. That's pretty much close, right? So you can already tell this is exactly the same person. In fact, you don't really need 1600. Well, is 25 enough? Perhaps not, right? So if you only use 25 components, it's not very clear if this is exactly the same person. It's clear that it's a person, but it's not clear if it's exactly the same person. But then if I use 200 components, let's say, or even 400 or somewhere between 200 and 400, pretty much all the important details of this person, specific to this person, is also captured in some sense. So you only need something like 300 directions to capture this person's, essential features that we need to say if this is the person or not. You don't necessarily need all the way to 1600. Well, if you go to 1600, you are adding more and more finer details, right? So maybe there are more details about how the face is, how the eyes are, noses and so on, which is perhaps not necessary to really say if this is the same person or not. Only 300 numbers are sufficient, right? So which means to say that the original image had 32,000 pixels, but now what are we saying? We're saying that, well, just 300 numbers, you can perhaps recognize each of these persons pretty well. You don't need 32,000 numbers, right? So that's like 100 times a gain that you can get by doing this PCA. Well, here is another way to look at this. So here is a different image which is not characteristic of the data set from which you are running PCA and getting the principal components. So this is a dog image, right? So now this also has 32,000 pixels. Now what are we doing? We are only taking the top 25 and trying to reconstruct this dog. The proxy for this dog in that 22,000 dimensional space that best represents this dog. But because the 25 directions, the 25 dimensional space that best represents the dog, that's what we are trying to find. And because these 25 directions are the top 25 directions with respect to human faces, if we are trying to project our dog onto this 25 dimensional human space, you are not really going to see the dog reconstructed that well, right? So you are only going to see something like, you know, the best human representation of this dog, right? So that's what you are essentially getting, right? So you are not really getting the dog reconstruction that well. Now as you keep going, so for r equals 100, well, it's still not that good. For r equals 200, it's still pretty bad. 400 is pretty bad. 1600 is still okay, right? So when you have 1600 dimensions, then the reconstructed dog pretty much looks like the dog. Now the point I'm trying to make here, and this is important in understanding what is happening here, is that because the data set on which we got these principal components from contain only human faces, it is trying to capture the most important directions with respect to human faces. Which means if you start with some other, a dog's face or even a tree, you're not going to get good reconstruction with small number of principal components. So if your goal was to distinguish a man or a face, man or a woman from a dog, right? So a human from a dog, then you don't necessarily perhaps need even 200 components. I mean, even very small number of components is good enough. Even with 25 components, you can say if it's a human face or a dog's face, right? So because the dog's face is on the 25 dimensional subspace looks nothing like human or nothing like dog. So you still might get some distinguishing capability. On the other hand, if you really want to say it is this particular human, well, you still don't need 1600, right? So you only need something like 200 to 300. But then with 200 to 300, the dog does not look anything like the dog yet. With 1600, you are somehow able to reconstruct both the human faces and the dog's face correctly, right? So which means there is enough information in the top 1600 directions that can represent perhaps any face, right? So anything that has a eyes, nose and mouth perhaps is captured in that 1600 dimensions, right? So you don't, now you won't really be able to, you know, I mean, the dog looks like the dog, the human looks like the human, right? So with 1600, you kind of get most of the information. Whereas if you took a tree, perhaps you would need much more dimensions to reconstruct the tree. 1600 may not be enough. Or if you just took a random image, right? So an image where each of the pixel values was absolutely random. Now, how many dimensions do you think you would need to reconstruct this image? Of course, the image does not have any structure. So it won't even be possible to say if the reconstructed image is similar to the original image or not. But then if you want to exactly reconstruct this, you would need all 32,000 dimensions. But remember, if you have 32,000 dimensions, you can reconstruct any image, right? So because you have complete information, right? So for any set of 32,000 dimensional vector. What we are asking is, with smaller numbers, when can you reconstruct well? Well, if it's a human face, you can reconstruct well with just 200 to 300 dimensions. If it's a dog face, you perhaps need 1500 to 1600. If it's a tree, maybe you need 2000, 3000. I don't know. I have not tried it on this data set, but that would be my guess. But if it's a random image, you would need more, right? So 32,000 in the worst case, right? So you would need to store everything. So this is a very good example of PCA, which is called the Eigenfaces, which can recognize faces, specifically human faces. Of course, we will use this as like a pre-processing technique to store only the top projections on the top few eigen directions, and then use it later to train a supervised learning algorithm. That's the basic idea. So given a new test image, you will again project it onto the top few eigendirections with respect to the human faces, and then run your supervised learning algorithm to see if you got the correct answer or not. And because this works, because there is some structure to these natural images, right? So there is some underlying subspace, that's the technical word to use, right? So there is some underlying linear subspace where most of the information is captured of the human faces, and so this algorithm works. Okay, so that is a nice example of an application of PCA. There are many more, and just wanted to show you one example. Now let us continue our discussion to understand what are some shortcomings of the PCA algorithm itself, and how we can fix those shortcomings. And as I said, the more we'll try to understand these shortcomings and then try to fix them, that will lead us to something very, very interesting, which is useful more in general for machine learning applications. Okay, so the next thing that we are going to look at is issues or concerns with PCA. So we'll point out two main issues or concerns with PCA, and then try to fix both of them in the course of time. And the first issue, it's not like a problem, but then it's like a concern, definitely, is the time complexity. Right. So how much time does it take to run PCA, right? So we have an algorithm. As computer scientists typically are, you should care about how long would it take to run this algorithm. So what is the most time consuming step in PCA? Well, PCA is just constructing a covariance matrix and then computing the eigendirections of it. So finding the eigenvectors is the time consuming step. Finding the eigenvectors and eigenvalues of covariance matrix. Now there are a lot of special purpose numerical linear algebra solvers which can perhaps do this in the most efficient way possible. But what I am going to suggest now is a general time taken for finding the eigenvalues and eigenvectors of any matrix, in particular the covariance matrix, right? So we care about the covariance matrix, which is a D cross D matrix. And typically, right, so I say typically because of course there might be special purpose softwares which do this faster, but usually it takes order of D cubed time, right. So this is the time complexity. If you're not familiar with the order notation, that's fine. So you can think of this as D grows, D is the dimension of the data set, grows, the time taken grows cubic in D, right. So it will be order of D cubed. So this is a problem, this is an issue when D is large, right. So when D is large. So question is, if D, the number of features is large, for instance in the Eigenfaces applications that we saw, the number of features was around 32,000, the number of data points was smaller than the number of features, was only perhaps 20,000 or something like that. So if the number of features is large, D is orders of tens of thousands or even millions, then D cubed is going to be million cubed, which is huge, perhaps huge for computing these eigenvectors and eigendirections, right. So an example of where this can happen is face recognition. Face recognition, eigenfaces, right. So that we saw where the number of features was 32,000. This is problem number one. So we won't really say at this point how to fix it. We will talk about this in a minute, but then I'll point out one more issue and then revisit this. Okay, what is problem number two? Problem number two is an unrelated problem to problem number one, at least at this point it will feel like that. This is issue 2, which is, so what is PCA trying to find? PCA is trying to find some linear combination of these features which are very important. So, if there is weight, if there is height, maybe weight plus height is a very important feature, or weight 2 times weight plus 3 times height is very important, and things like that. But perhaps let us say you had weight, height and something like a body mass index or something like that. Now, the body mass index might not linearly depend on weight and height, maybe it is something like weight over height squared. I might get the formula wrong, but then there is a quadratic dependency with respect to how the body mass index is related to the weight and height. So, it is not linear, right. So, which means that if we, for instance, if we plot in 3D feature 1, feature 2, feature 3, and let us say we observe that the data points fell something like this. Now, what am I trying to allude to here is that it could be the case that you have some manifold or some curved space which is in your which is a subset of your original space, which is R3. So, this is a curved space, and all your data points lie along this curved space, let us say. Now the fundamental structure in your data is not a linear structure. Why is it curved? It is curved because these features themselves have a nonlinear relationship. Maybe F3 is F1 into F2 plus F2 squared or something like that, right. So, maybe in your application that is what is the fundamental equation that relates these features, or the most important equation. Now, this is a structure, just that PCA won't find this because PCA is not looking for these kind of relations. PCA is only looking for relations which are linear, right. So, how can you linearly combine? How can you weight each of these features, add them up and then create new features? Not all applications may have such relationships, right. In other words, so if you run a PCA, so you might get something, you will still get some output, right. So, you will get, let us say, if this is like a 2-dimensional manifold inside a 3-dimensional space. Let us forget the technical definition of manifold. It is a curved space for us, but then essentially think of it as a blanket which is curved and all the points are on this blanket. But now PCA, if you run PCA, you are still going to get some results, right. So, PCA might, there is nothing stopping us from running PCA on this. PCA might say that there is some plane which is the best plane that represents this data. Now, if you compute your error with respect to this plane for these data points, that error is still going to be high. It is not going to be insignificant, which means that we might be fooled into thinking that, well, there is a third dimension which is also important for this data set, and we might add one more dimension. Of course, then you will be able to exactly reconstruct this data set. If you have 3 dimensions, there is you cannot go further. You can reconstruct any data set, so your error will be 0. But then PCA will not know that there is a fundamentally, essentially a 2-dimensional structure that is hiding in this data set. Okay. So, the problem though is the issue is data may not necessarily lie or live in a low dimensional, and the keyword is not just low dimensional linear subspace, right. So, when I say subspace, I just mean you can think of it as two-dimensional planes passing through origin, or a line passing through origin, and the higher dimensional analog of those, right. So both of these issues that we have identified are relevant issues. One is time complexity. When the number of features is large, you have a time complexity issue. The second is when the features themselves are non-linearly related, then also you have an issue, right. So, both of these cases, in one case PCA will work, but then will take a lot of time. In the other case, PCA will work, but then may not give you the desired result that you really need. Here is a surprising fact, and this is perhaps the punchline of this video, is that we will have the same solution to both these issues. at this point, this might seem odd, right? So, these two issues do not seem related at all. One is a time complexity issue, the other is a question about the structure. And the surprising thing is that if you solve one, you have actually solved the other as well, in the sense that you can use the solution to one intelligently to solve the second problem as well. We won't break the suspense as to how that is done at this point, but what I will do is we will first consider issue 1, try to solve that, and then make some observations which will help us solving issue 2 also. So, let us start with solving issue 1 and how to go about issue 1.